There's a mathematician, very famous mathematician, that just claimed to have solved the Riemann hypothesis, which is a 160 years old problem. And the zeta function that he solves for is a relationship between primes and fine structure constant. So I don't know if you saw that announcement last week, but you should look at that lecture. It's not in a paper yet because it was literally just a lecture that he gave. Interestingly, much of that was already worked out by Robert Grant, which is on our faculty. And if you've been on the Robert Grant course
electives
that we produce here at the faculty, he would have talked about that. But yes, there's a direct relationship, not just with the fine structure constant, but with all constants relative to primes and relative to geometry. And Robert Grant is doing an excellent job on that. There's a relationship between geometry, prime numbers, and Q primes, and I mean there's some complexity there, and geometry, and all of the constants, not just the fine structure constant. So,
Nassim, what is the fine structure constant? If you would, that was the initial part of this question. What would you say that is playing some function in the universe? What is that?
Oh, okay. Well, you can think of it as the way, so the fine structure constants makes absolutely no sense if you don't have the Planck field. If you don't have an ether, it makes absolutely no sense. Like, what the heck? And that's why all this time, this scientific community is like, well, it's just a number we throw in and it comes out right. So, and it's, and so 1 over 137 is kind of like the thing. And it turns out that, like, if you, actually, it's not quite that. It's a little more, it has more resolution on it. But so you don't know where it comes from until you realize the atom, the electron, and the energy levels of the electron and the relationship to the fine structure constant is because you're looking at, basically, you can think of it as harmonic relationship in the structure of space, right? Like oscillation modes in the structure of space that are going to be very well defined. They're going to come out. So these fundamental constants, they just come out because there's fundamental relationship in the structure of space that defines these very specific nodes, if you'd like, interference pattern nodes in the structure of space that, which eventually transfer to our mathematics when we're trying to describe, atoms and electrons and all this stuff. It starts to come out, these fundamental constants, because the geometry of the field dictates it. So we notice when we make measurement that these values come out, and we don't know what they are and where they come from, but we know that if we plug that number in, our equations work, right? We call them constants, and they are constants because the structure of space resonates at very specific frequency, at very specific harmonic relationships. And they define these constants. So it's the geometry of the field, producing harmonic notes. So there's actually, you could think of it as like sound or frequency involved, right? Creating harmonic notes that defines what we call constants, because that's the other thing is that you got to realize the universe is not writing numbers. The universe is doing its thing. And then when we write numbers, we notice that there's patterns or there's something different about certain numbers and others, like prime numbers. So, but then we're discovering now, and this is very, very important, the work that Robert Grant is doing, the work that that mathematician is doing, describing the Riemann function, the Riemann hypothesis, but showing, and I think the Nobel Prize was just, or the Field medal was just given for somebody that just showed the direct relationship between mathematics and geometry and frequency. But you know, this is emerging now. It's very, very important. It's very exciting because finally we're tying fundamental constants with geometry and physics and mathematics all together, and because they're not separate, they're all the same thing expressed differently.